Cool, so let's get started. I'm Tanya, and today I'll be discussing Portunus. Is there like an echo? I don't know. Okay, we're good. Okay. Today I'll be discussing Portunus, which is a geographical key management system that has been deployed by Cloudflare. Okay. Yeah, and Portunus is built using attribute-based encryption, which is a variant of public key cryptography, and it allows us to do access control on customer keys. And to our knowledge, this Portunus is likely the largest attribute-based system that has been deployed at such large scale. So today, the main thing that I would like to do is try to convince you that ABE is, in fact, okay, this is, yeah, all right. That ABE is an excellent alternative to compared to the usual strategies of doing using a central party as an arbiter to enforce access control. And it's structurally very symbiotic with, how distributed systems operate. So let's kind of try to understand the problem. So TLS terminations, everybody should probably be familiar with TLS. It's a pretty popular protocol that's used to secure communication and protect data integrity between browsers and websites across the internet. And the idea is during a TLS handshake, the website presents a certificate that includes its public key, and it creates a digital signature using its associated private key and sends it to the browser, and then the browser is able to verify that digital signature and ensure that and confirm that the website is who it claims to actually be, and consequently create a secure channel to perform the communication. And the important thing to remember is that this private key is in fact very private and very sensitive, and this is what is going to be the problem that we're trying to protect. Okay, that's regular TLS. But website operators often seek out the services of infrastructure providers and CDNs like Cloudflare to improve performance and security. But in order to provide those services, so for example, caching, infrastructure providers need to be able to inspect the TLS connection between the browsers and the client, between their customers, users, and their customers' websites. And this TLS inspection is called TLS termination, and it requires the provider to be able to access the customer's private key. So let's work through an example. So let's assume that you have that a bank that's based in the European Union is a customer of Cloudflare. As we saw before, Cloudflare would need access to their private key in order to terminate TLS for them. So they bring their certificate and their associated private key. They upload it to Cloudflare. All the traffic goes to the control plane, which is responsible for handling API traffic. And the control plane then encrypts their private key with a master key that is shared amongst all edge data centers. It then puts the wrapped private key into Quicksilver, which is Cloudflare's globally synchronized key value store that's used to distribute customer configurations to the edge. So the thing to note here is that every edge machine has gotten a local copy of this customer's key, and that may be a problem. So let's say that this bank only wants its key to be accessible in the EU. What are our options here? And this could be for compliance reasons. It could be for, whatever reasons. So the standard way to solve this problem is to just have a very centralize all the access control logic and place it in core. But Cloudflare has invested a lot of effort into building this very large and very distributed edge data center network. It kind of defeats the point if like every single time you have to make a TLS connection, which is really very critical for like any user interaction with any customer's website, that you have to go to the core or like the control plane in order to like do that access control. And there's a reason that we built Quicksilver or the globally synced key value store in the first place. We need its ability to provide the edge lower latency and high availability and fault tolerance and all those great things. So another option could be, okay, let's just send the keys, or let's just wrap the key and send it only to EU-based data centers. Well, there's not really a way in Quicksilver's replication strategy that lets you customize where you send it. It broadcasts everything like to everyone. And if we were trying to build something like this, it really ends up challenging fundamental design assumptions that Cloudflare has made over the years that assume that every machine has the same copy of the Quicksilver dataset. So this is not really practical. The third option could be to use public key crypto in a more naive way. So what if instead of using the same key to encrypt the TLS, the customer's key, the same master key to encrypt the customer's keys, we issued every single edge data center its own unique key, and then we encrypted to each of the authorized data centers that would belong to some policy. So in this case, we would encrypt to like every single EU data center. But this does not scale very well, and in terms of storage is not really the best, because now so when you start going into like the millions of customers range, like this really blows up. Okay, so what can we do? So as we were sort of thinking about what our solution should look like, we drafted a set of informal constraints that we would like our solution to provide, and you guessed it, ABE was our answer to these. Key rotation we have to build on top, but yeah. So quickly, the variant of ABE that we use is ciphertext policy ABE. And this is the more natural form of doing access control or expressing access control. And basically what's going on here is you have a message that's been encrypted under a policy, which is country US or region EU. And any user that has the right set of attributes that satisfies the policy is able to decrypt it. So in this case, both US and EU are able to decrypt the message, but country Brazil could not decrypt it. And you can do a lot more than just ORs. You can do ands and nots and compose things however you want. So it's pretty flexible. All ABE schemes are not created equal. There's a wide variety of schemes out there, and we want to select those that satisfy some characteristics that we would like to have. So the most important one is negation. All ABE schemes give you and ors out of the box, but schemes that express negation in a natural form are less common. So yeah, this is something to look out for. And there's also like different types of negation, and you have to sort of understand what you're looking for. But for access control, there's like one common form that you look for. And this is very crucial to us because we would like to be able to exclude regions or exclude some sets of data centers. So this is definitely non-negotiable. Large universe, so this has two components. So one is you can select an arbitrary string for your attribute label. And then the second component is that you don't have to predetermine the set of attribute labels out of the box, like when you instantiate your scheme. So let's say that there's like a new regulatory standard that comes up, and I want to create a policy that includes it. That's something that you can do at a later stage. They don't have to be determined upfront. Repeated attributes, this is super nice to have. You can compose nice policies, more flexible policies. And then security against chosen ciphertext attacks. So this is just a strong variant of security. Yeah, I won't go into much detail there. So we ended up with this scheme that we selected, and again, refer to the paper for this because this would take a long time to explain. But yeah, the scheme satisfied all our constraints, and we're pretty happy with it. All right, let's look at the architecture. So, so to start off, we have the key generation authority that holds the master secret key, and it's responsible for issuing attribute secret keys that are used for decryption for each edge machine. And it validates the set of attributes that each machine possesses using a machine provisioning database that maintains a map of attributes to of machines to attributes amongst other properties. And this key generation authority is placed in a very restricted environment in the core, and the machine provisioning database is also very highly restricted and cannot really be modified by pretty much most people. Encryption is pretty simple. Customer uploads their certificate, they specify their policy, it goes to the certificate manager in core, which wraps it with the master public key under their chosen policy, puts that into Quicksilver, which broadcasts it out to everyone. Decryption. So when a user is trying to access some website, they make an HTTPS request, and this request is going to land at the data center at the Cloudflare data center that's closest to it. There's a TLS termination service there that first tries to fetch from Quicksilver the ciphertext, which is the encrypted version of the customer's website that the user is trying to go to, and if it has the right set of attributes, it's going to be able to decrypt that and therefore do the signature and terminate the handshake. But if not, then it will proxy that request onto a data center that does in fact have the right set of satisfying attributes, and whoever is able to decrypt the key terminates the handshake. So for performance, we really care about decryption performance in particular because that's the main thing that's in the critical path of requests. We are showing numbers for a policy size of 50 attributes, but in practice, it doesn't go beyond 3 to 4 for our situation. So these numbers are even better. But as you can see, there's definitely a bit of overhead here that could be problematic. So our antidote to this question is policy keys, and like all of computer science, you can solve a problem by adding another layer of indirection. So if you have any familiarity with public key crypto, you don't usually use RSA keys in order to encrypt large swaths of data. Instead, what you do is you have a symmetric key that acts as your data encryption key, and you encrypt the symmetric key with RSA. And that's because public key crypto is just significantly slower than symmetric crypto. So we're kind of doing a similar thing here where we're using elliptic curve key pairs, which are not symmetric keys, but they're still really, really fast. In order to, we have a one-to-one mapping between these policy keys per unique policy, and that's what we use to encrypt all the customer keys that have the same policy. And the reason that we don't go with something like a symmetric key is because we want to maintain the property of having public crypto because it allows the certificate manager to encrypt without having to access keys. And so by combining it with caching and policy keys, we're able to reduce decryption cost. This also helps us with key rotation because the number of policies is much lower than the number of customer keys. So we can get away with not having to rewrap all customer keys when we create a new generation of keys. Instead, we just need to rewrap the small handful of policy keys. So challenges, if this is so good, why aren't people using it? So to start with, it's still fairly new. Like the existence of an efficient and usable scheme that satisfies all these properties is still relatively recent, even though work in this area has been going on for like 20 years plus. And we found this because in 2016 we created we were working on a predecessor of Portunus, and we realized that there were no efficient ABE schemes that supported negation. So what we ended up doing was simulating ABE with a combination of two other public key variants of cryptography, which are called identity-based encryption and broadcast encryption. But this was theoretically problematic because collusion resistance is the property that makes it hard to build ABE schemes in the first place. And it still was inflexible. Next, translating a dense cryptographic paper into efficient code is pretty burdensome. And it's not only the notation or the steps that are being taken, but also some of those steps can conceal significant computation. So you have to be careful. Choosing parameters. So trying to understand what a particular cryptographic parameter means for your application is always a challenge with like security and cryptography in general, but here, because of the lack of prior art, that's more of an issue. Pairings, so pairings are the mathematical operation that underpins ABE, and they are more unfamiliar to people compared to all the traditional stuff that's out there. And it's also not been standardized by NIST, even though there's a lot of talk and a lot of discussion to do so. Okay, it'll hopefully show up. Path to post-quantum, I won't go into it. Lessons learned. So main thing is ABE is too slow. This is something I've given this talk at Real World Crypto, which is a venue where people talk about real world crypto deployments, and this is something that you just encounter every time you talk about ABE, like, hey, isn't it too slow? But that's really not true anymore. And especially when you use it like you use public key encryption, when you use it in a hybrid way, it's definitely very applicable for many applications. Next is, so if you're going to deploy a complex cryptographic piece of code in something as critical as TLS termination, you really need to make sure that every other component of your system is as simple as possible, because it might not be the cryptography that breaks, but when there are other stakeholders and SREs that, yeah, it might get scapegoated. And so you want to conserve all complexity for the crypto, make everything, it's very prudent to make everything as simple as possible. Key rotation, yes, should be simple and automatic. So key takeaways, yeah, consider using, so I believe that ABE is criminally underutilized for performing elegant access control in distributed system settings. And the lack of prior art is definitely a problem, as is the lack of standardization, but there's also a bit of, well, nobody really knows about it. That's another issue. So that's kind of why we wanted to publish this paper in this venue, kind of try to bring it to more people. But again, it's a two-way street, right? Like, if there's not as much demand, there's not going to be more efforts dedicated to standardization. That's basically it for me. If anyone has any questions, yeah, definitely feel free to reach out. The code, we have open sourced our library. It's part of Cloudflare's cryptographic primitives library circle. So yeah, cool.